Yeah, I can already see it on YouTube now.
Yeah, okay, good. Okay, perfect. All right, so we'll just start in a minute or two. Okay, so Alexey, if you're ready, we can start.
Yeah, I'm ready.
Okay, so thank you everyone for joining us. This is online Spintronics seminar number 125. Our speaker today is Professor Alexey Kovalev. It's his second presentation in the series. Alexey is my colleague at the University of Nebraska-Lincoln. He received his master's degree from the Moscow Institute of Physics and Technology in 1999, and his PhD from the Delft University of Technology in the Netherlands in 2006. Then he had two postdoctoral appointments, first at Texas A&M and another one at UCLA. And then from 2010 to 2013 has been an assistant project scientist at the University of California at Riverside. So he's been at UNL since 2013, where he climbed up the ranks from assistant to full professor. His research is in condensed matter physics and also in quantum information. He received the DOE Career Award in 2014, and he is an author of more than 90 publications, a lot of them in spintronics and in decoherence in quantum systems and error correction. So his talk today will be on new platforms for the realization of topological spin textures. And Alexey, you can take it over from here. I look forward to your talk.
All right. Thank you, Kirill. Thank you, Shane, for letting me talk at this nice venue. It's always a pleasure to give a seminar here. And today I would like to talk about new platforms for the realization of topological spin textures. So this is the content of my talk. So I will give introduction, then we'll talk about magnetic textures in ultramagnets. I will talk about topological spin textures and their connection to spin superfluidity, and I will also talk about other platforms where topological spin textures can be realized. All right, so let me begin with introduction, and let me start with topology, which is a mathematical concept, and it distinguishes objects that cannot be transformed into each other with continuous transformations. So you can see on the left, object is being continuously transformed, and yet it can never become the object on the right, which is also being continuously transformed. Then this topology then modifies the properties of such topological objects. And here you can see a simple example how, for example, such topology affects certain properties. In particular, it is known that every continuous tangent vector field on an even-dimensional sphere must vanish at some point. And the key word here is sphere, because sphere has certain topology. Then if we consider torus, which has different topology, then we can find such continuous tangent field to cover torus. So here you can see that clearly there is a difference. In physics, we are also looking at such differences, and we can also identify various topological objects. So the simplest object that we can probably realize in magnetic systems would be a domain wall, which can be realized in a magnetic wire, and it goes from one direction of magnetization to another direction of magnetization. And we can achieve that in different ways. In particular, we can rotate magnetization along this axis, that is the direction of the wire. And in this way, we will obtain what is so-called block domain wall. And if we apply this rotation along axis that is perpendicular to the plane of the system, then we can realize so-called Niel domain wall. Now, you might ask, how are these objects connected to topology? So to connect them to topology, we would need to consider 1D system, and we would actually need to confine magnetic moments to be 2D magnetic moments. Then, for example, on top, we can realize this wire, where magnetization essentially performs full rotation. Then, if there is such wire with, for example, periodic boundary conditions, or if left and right magnetic moments are fixed, then there is no way to unrotate this type of configuration. So clearly here we have non-trivial topology. While in the lower wire, the rotation first goes one way, but then goes the other way. And you can imagine that here we can unrotate this system by performing continuous operation, just like I mentioned in the beginning. So as a result, the object below is trivial topologically. And we can also assign topological charge. So then, of course, you might ask, how can we achieve 2D magnetic moments? So here, to achieve this in physical system, we might need to involve easy plane anisotropy, where that anisotropy would confine magnetic moments within the plane. Now, if we increase dimensionality, then the options, the number of options increase. And in particular, then we could consider a plane, such as here. And this time we can consider an ordinary three-dimensional magnetic moments and realize what is called skyrmion, which goes from up to down as we go from outside of skyrmion to the center of skyrmion. If we consider cuts of this skyrmion, then here we will see this type of Niel rotations, which should remind you of topologically not trivial systems that I mentioned in the previous slide. However, options here are more multiple, and in particular, we could also construct the system shown on the right, where as we consider these cuts, this cut, this cut, this cut, and this cut, we see that we get Niel type rotation, then we get block type rotation, then we get reversed Niel type rotation, and then we get reverse block type rotation. So clearly there is some topology going on here, and in fact there is. Furthermore, these are topologically protected systems. The left one is called skyrmion, the right one is called anti-skyrmion. And actually, to stabilize such type of systems, we do need extra type of interactions, such as Zoloshinsky-Mori interactions, because usually this system live on a lattice, and that's why we do need to involve additional types of interactions. Furthermore, the Zoloshinsky type of interaction can fix our skyrmion to be either Niel type on the left or anti-skyrmion type. So to characterize such structures, it is convenient to introduce a topological charge, which is here, and it essentially counts the solid angle that magnetic moments accumulate while we go through the structure of skyrmion. And the best to see that, we could perform stereographic projection of our plane of skyrmion onto a unit sphere, and then the magnetic moments will exactly cover this unit sphere. And this would happen, for example, for Niel skyrmion in the middle. And now if we apply global rotation along z-axis by 90 degrees, we can go from this type of covering to this type of covering, which corresponds to Bloch type skirmion. We could also perform additional operation where we could perform mirror, but mirror would not act on magnetic moments. It would only act on coordinates of those moments. Then it would modify the spin field here in such a way that the covering becomes this interesting covering, and it actually covers, the topological charge becomes negative and -1 compared to the two topological charges on the left. So overall, this shows that we have a lot of possibilities with magnetic systems, and I will discuss this type of structures in my talk. And let me begin with domain walls. And here I'm interested in, for example, dynamics of domain walls and different types of domain walls. And here again, I'm showing you Bloch domain wall and Neal domain wall. And it is convenient to parameterize such domain wall in terms of unit vector. That is, again, in turn parameterized in terms of spherical coordinates, two angles theta and phi. So then it is not hard to notice that for Bloch domain wall, angle phi is actually fixed to be pi½ in such a way that as we go along this domain wall, the x component of magnetization is always 0. For the Neal domain wall, my component is 0, and phi angle has to be 0 as well. So we can then find the solution for the domain wall, and if we consider energy functional, where here I used exchange interaction proportional to A, and the easy axis anisotropy proportional to Ku, then if I use this type of parameterization, then the energy functional takes this simple form. And as you have noticed, angle phi dropped out from this energy functional. So we need other types of interactions, such as dipolar interactions, to, for example, fix the angle phi. But for the angle theta, we actually obtain a nice solution. So first, we write Euler-Lagrange equation and solve it with this function written below, where I also introduce the domain wall width, which is the square root of A over K. Now, we are also interested in the dynamics of domain wall, and here we would need to involve the Landau-Lifshitz-Gilbert equation, which is written here, where the last term is Gilbert damping, which damps the dynamics of magnetization, while the effective field is defined the field around which the magnetization precesses, and it can be expressed again in terms of that energy functional that I wrote earlier. Now, a typical approach for domain walls that move relatively slowly to use the ansatz that we found in the previous slide for the angle theta and modify it by introducing here the coordinate of the domain wall Q of t. And in general, delta of t could also be, in principle, in some cases, considered as some coordinate. But in general, delta is treated as constant. And if we then plug this type of ansatz into LLG equation, we obtain these two equations written below. So one of these equations then governs the velocity of the domain wall, which is q dot. And clearly, if we apply magnetic field, we can drive the domain wall. While the second equation governs the precession of the domain wall, which essentially here is blocked by this term hk. And this term hk I actually introduced here, but it could, for example, and I didn't introduce it before, but it could correspond, for example, to dipolar interaction, which for a wide enough wire would fix the domain wall to be Bloch type. And they would block all the possible precession of the domain wall, at least below the Walker breakdown. So then, okay, so clearly from this we can have some dynamics of domain wall. And why I brought it here, because this will actually be relevant to ultramagnets where the HK dipolar field will either be absent or will be very small. And as a result, as we will see, this precession of domain wall will be more important. Okay, so there are other ways to control magnetic textures, and that would be through spin transfer torque physics, which is summarized in this cartoon. If we have spin polarized charge carriers, and if they go through the ferromagnet, then close to the interface, they become repolarized and exit ferromagnets with a new direction of polarization. Now there is angular momentum, which is clearly not conserved for charge carriers. It has to go somewhere, and it actually goes into magnetization. So as a result, there is a so-called spin transfer torque acting on magnetization, and we can use this torque to manipulate magnetization. So this type of dynamics also extends to systems with magnetic textures, where what happens here is that we have a series of such polarizers, and when charge carriers pass through this magnetic texture, they are constantly in need to repolarize themselves. And as a result, the angular momentum again has to go somewhere, and it goes into magnetization. And we end up with a torque, so-called spin transfer torque, acting on the magnetization. So to describe this torque, we need to modify the Landau-Lifshitz-Gilbert equation, where we introduce two extra terms. So as I mentioned, the angular momentum needs to go somewhere, and it results in so-called adiabatic spin transfer torque, written here as the first term. And then, as you probably noticed here, the charge carriers are not able to perfectly realign themselves, and there is slight mistracking. And because of this slight mistracking, we get the extra correction, so-called non-adiabatic spin transfer torque. So this leads to a torque which is orthogonal to adiabatic spin transfer torque. And again, we use extra parameter beta to parameterize it. And overall, also, we parameterize both torques in terms of effective spin drift velocity, which essentially introduced here. And it is some parameter which depends on material parameters and proportional to the charge current. So essentially, we can use charge current to control magnetic textures according to this equation. So let's see how this actually works. And again, I use the main volt to show this. So I take my ansatz and I plug it into LLG equation from previous slide, and then I get slightly updated equation compared to the previous equation. Again, let's look at the first equation here. And we see that beta U appears here in the right-hand side, and it can drive the domain wall in a similar way as Hz can drive the domain wall. So the non-adiabatic torque then can drive the domain wall. Let's look at the second equation. And here we get an extra term which is proportional to U, the last term. And this term, as you remember from the previous slide, corresponded to adiabatic spin transfer torque, which means that the adiabatic spin transfer torque can induce precession of the domain wall. And this, again, let me repeat this, will be particularly important for altermagnet, where HK term will be absent due to very small or absent dipolar interaction. And as a result, this spin polarized current will actually be able to induce precession of the domain wall. And that in turn can actually modify the dynamics of the domain wall, the velocity of the domain wall according to the first equation. Okay, the same type of physics also works with skyrmions, and this type we need to take ansatz of the skyrmion, which, for example, could be a 360 domain wall, and we need to plug it into LLG equation that I wrote earlier, and we will get this TL equation. So the first group of terms here are so-called non-dissipative type of terms or gyrotropic terms, and here you can see spin drift velocity U, and V would be the velocity of the skyrmion. And G here is the gyro tensor, which is essentially proportional, which is 4 pi times the topological charge of skyrmion. The second term is dissipation term, which is naturally proportional to non-adiabatic spin transfer torque and to the Gilbert damping, and there is also a term proportional to Gilbert damping. So here again, I remind you that V here would be the velocity of the skyrmion, and D here is dissipative tensor, which for typical textures is of the order of 1. Now, this behavior was confirmed in experiment where essentially what we should expect here is that there is a longitudinal motion of skyrmion with velocity proportional to u. And then there is a transversal motion which arises due to dissipative terms alpha and beta in the LLG equation. And here you can see that indeed skyrmions have a longitudinal and transversal motion. And transversal motion is usually referred to as skyrmion Hall effect. And this type of physics, again, will be important, will be relevant to altermagnets. All right, so let me then move to next topic, to altermagnets, which are a new class of materials suitable for spintronic applications. They combine fast dynamics of antiferromagnets with spin splitting effects. There are many possible applications, and they can also realize magnetic textures, and that's what is of interest for me. So let me first define altermagnets. So here I would like to separate them from conventional antiferromagnets, for which we typically have a combined translational and time reversal symmetry, or inversion and time reversal symmetry. Then if we act with such symmetries on the band of antiferromagnet, we will get another band with reversed spin, which immediately tells us that the band has to be double degenerate, as it is shown here, and which is a limitation for spintronic applications because this will clearly create difficulties in exciting spin polarized currents. To solve it, we could in principle induce spin orbit interactions, and that might help in certain situations. However, another solution would be to use altermagnets. And altermagnets also have two sublattices, which can be termed as spin down sublattice and spin up sublattice. And they are interesting because the non-magnetic environment of each of these magnetic atoms is actually different, as you can see from this plot. And in particular, this translates into symmetry, where the symmetry of this would be C4Z T1/2, so where we rotate by 90 degrees plus half unit cell translation. But then this would change one sublattice into another sublattice, so we would need to compensate for that, and we could do that in this perfect situation by additionally applying C2 rotation in spin space. So clearly, here we use these symmetries in order to design a version of antiferromagnet which actually has useful properties for spintronics. Let me also show you how this works in essentially 2D projection of this type of physics, where again I'm considering a lattice with magnetic atoms, up and down magnetic atoms. And again, as you can see, the non-magnetic atoms here provide different environment for two sublattices. And as a result, if we apply 90 degrees rotation, effectively we flip this environment for one sublattice into the environment that we would expect from the other sublattice. So as a result, we could say that here we have this rotation C2 times 90 degree rotation, where C2 is only in spin space. And why this type of symmetry is interesting? Because it does not forbid spin splitting any longer. It does put some constraint on the band structure. In particular, spin splitting along x-axis should be exactly minus the spin splitting along y-axis, but overall we can have k-dependent splitting for such bands, and this is very useful for spintronics. So now let's apply charge current along 1, 0, 0 direction. Then this would modify the Fermi surfaces such as shown here, and this would induce a pure transversal spin current, as it is shown here. Now, if we apply charge current along 1, 1, 0 direction, then this would induce spin current along charge current. So clearly, in this type of system, we can excite spin polarized current, and I am asking a question, then what happens if we have magnetic texture, such as shown here? Then this spin polarized current, while flowing through the texture, will have to readjust to local magnetic environment, and it will have to repolarize. So the charge carriers will be constantly repolarizing, as it is shown here. And the angular momentum will need to go somewhere. As a result, if you write LLJ equation, where here I write it in terms of two sublattices, we should get so-called adiabatic spin transfer torque, which is written here as this first term and second term. In fact, to be honest, even in ordinary antiferromagnet, we can have adiabatic spin transfer torque, but due to the constraints of ordinary conventional antiferromagnet, U1 has to be equal to U2, while in an altermagnet, U1 does not need to be equal to U2, and that exactly leads to this interesting physics that I will discuss a little bit later. Furthermore, we can also, by analogy, introduce so-called non-adiabatic spin transfer torque, where similarly, due to this mistracking, we should expect this type of torque to be present. And again, in case of altermagnet, U1 does not need to be equal to U2, in contrast to conventional antiferromagnet. Now, we could also write a model of, for example, thin layer altermagnet, taking into account the symmetries, and in the long wavelengths limit, the model that we can use is written here, where essentially we have two layers, A layer and B layer, and they are antiferromagnetically coupled with each other, while the in-plane exchange interactions are anisotropic. So Jx is not equal to Jy, and in the other layer, Jx and Jy are reversed. And we also consider anisotropy. So in the long wavelengths limit, I can actually use this simple model to describe, for example, domain wall dynamics and so on, and that's what we actually did. If we start with the skyrmion, then we immediately observe interesting behavior that skyrmion is actually associated with creation of magnetization density. While if I repeat this calculation for a conventional antiferromagnet, I will get zero magnetization. Now, of course, if we move skyrmion, then it will elongate and it will naturally induce magnetization density, which will actually, this time, will be a combination of this static magnetization density and magnetization density, which will arise due to the motion of skyrmion. So in principle, one can try to observe this. But we were mostly interested in different type of behavior where this spin polarized currents can actually be used to manipulate skyrmions. And here I chose this 110 alignment of charge current. Then in this case, the spin polarized current will be going along this 110 direction, and it will induce an additional torque, which we can summarize in terms of how it acts on two sublattices. So I call this torque SSTA, spin splitter torque adiabatic, and as you can see, it acts in the same direction for both sublattices. So as a result, it will induce the skyrmion Hall effect. In an ordinary antiferromagnet, we still have such type of effect, which is called here as STTA, spin transfer torque adiabatic, but it acts in opposite directions for two sublattices, and that's why in an ordinary antiferromagnet, we should expect zero skyrmion Hall effect. Okay, so here these results are summarized in this formula, so I can analytically derive the velocity of skyrmion in an altermagnet, and the first term is actually just should be familiar to you. This term essentially arises in a conventional antiferromagnet, and it tells us that we can drive skyrmion along current direction, and this motion happens due to non-adiabatic spin transfer torque, which is just U beta, as I showed you earlier in the LLJ equation. But in addition, we get second term, this one and this one, which induces skyrmion Hall effect, and this torque only arises in altermagnet. Now, in this plot, you can see the x and y components of the velocity, and if the alignment of charge current is along 110 direction, here you can see a very large skyrmion Hall effect. Now, if you align it at 45 degrees, then skyrmion Hall effect becomes zero. So from this, we can also see that we actually we're having here an isotropic skyrmion Hall effect. Now, also, if you look at magnitudes of the velocity, we can actually drive this fermion very, very fast in the transverse direction, much faster compared to the longitudinal direction. And that happens because actually it is known that non-adiabatic spin transfer torque is not so efficient at driving fermions in antiferromagnets, where usually people use spin orbit torques. But here there is alternative to exploit the spin splitter torque in order to induce fast motion of fermions. And here in these plots, you can see that we have perfect agreement between analytical description described by curve and dots describe numerical calculation based on the model that I showed you earlier. Now let me move to domain walls. And in case of domain walls, I already mentioned it, that the precession of domain wall should be important, which actually turned to the fact that for phi, we need to use a more complicated parameterization. So it is not just enough to use phi of t, but we need to introduce this more complicated parameterization, which actually turned out to work well. And furthermore, phi here, phi of t describes the precession of the domain wall. So the domain wall precesses even at small currents in ultramagnets. The domain wall width also behaves interestingly. It is written here. And in contrast to conventional antiferromagnets, we do not see here so-called Lorentz contraction, but due to additional term here, we have more complicated domain wall width behavior. So this actually summarized in this plot, where this blue curve shows you this gradual increase of domain wall width, which is in contrast to domain wall width contraction. Now, the precession, the origin of this precession is actually easy to understand. So the spin polarized current passes through the domain wall, and it has to dump angular momentum somewhere. In case of ferromagnetic domain wall, it can dump it into magnetization, but in case of antiferromagnetic domain wall, basically there is no mechanism to dump this angular momentum. So what happens is that domain wall starts to precess, and it dumps this angular momentum into lattice through domain wall precessions through Gilbert damping. And this has also strong effect on domain wall velocity. In particular, here we chose a regime in which this effect becomes the strongest. And here you can see, as we increase the charge current, the domain wall at some point stops increasing the domain wall velocity, and it's actually the domain wall velocity drops. And this happens due to very fast precession of the domain wall. Now, we could also have here anisotropic behavior, because clearly, if we want to have spin polarized current flowing along the domain wall, we would need to align the charge current properly. In particular, it has to be aligned along 110 direction. And in this case, we have substantial domain wall slowdown due to this domain wall precession. However, if we choose 45 degrees orientation of current or 100 direction, then the spin current is flowing in the transverse direction, and it's not dumping angular momentum into domain wall any longer. And as a result, we observe a fast domain wall dynamics. And here overall, we get this anisotropic behavior. All right, so let me conclude at this point. So we have developed a theory of spin splitter torques in textured ultramagnets. Spin splitter torque substantially modifies magnetic texture dynamics, leading to domain wall precession and anisotropic Skyrmion Hall effect. The behavior exhibits features that combine characteristics of both ferromagnets and antiferromagnets, allowing efficient control of magnetic textures, and ultramagnetic textures exhibit anisotropic features originating from their essential D-wave symmetry. All right, so let me then switch gears and move to the next topic, where I would like to discuss topological spin textures and spin superfluidity. So let me first remind you of spin superfluidity, which can be realized by taking the familiar energy density that I considered earlier, where we have exchange interaction. However, the sign of anisotropy here is opposite. So instead of easy axis anisotropy, I have here easy plane anisotropy. So the magnetic moments are confined within the plane. And here it is convenient to parameterize magnetization in terms of in-plane angle phi and small out-of-plane component mz, such as shown here, for example. Then if I plug this parameterization into this energy density, I can again derive Euler-Lagrange equations. I can also introduce here Gilbert damping. And overall, I get interesting modes here where the phi angle can constantly increase. So there will be in-plane precession of those magnetic moments, and mz component will be constant. However, of course, the Gilbert damping will essentially eliminate such type of dynamics. So to maintain these dynamics, we would need to constantly inject spin polarized current with Z polarization, and that will maintain this in-plane rotation. And in this case, we can have such type of modes. So what's interesting about such modes is that they are able to carry spin current, and also they, if we consider the decay of this spin polarized current, then it will have algebraic decay. So potentially we will be able to propagate this spin signal over longer distances. However, such type of modes or solutions will be fragile. And for example, if we have some in-plane anisotropies, then clearly this type of physics will be modified. So instead, then we decided to consider a system where we, from the beginning, have anisotropy present in the system. So here there are two types of anisotropy. So first anisotropy is K, capital K, and it essentially confines all magnetic moments in ZX plane. And in the introduction, you have seen that such type of confinement can be useful because that confinement essentially turns our magnetic moments into 2D magnetic moments and allows us to talk about topology in the context of the main wall. And that's what happens in this situation as well. In addition, we have anisotropy described by kappa, and this type of anisotropy essentially stabilizes the domain walls in our system. So then we can have four types of domain walls depending on how they rotate. So for this sense of rotation shown here, we assign topological charge -1. Then there is this domain wall with the same sense of rotation. It has the same topological charge -1, while the other sense of rotation has opposite topological charge. And what's interesting is that under large anisotropy K, this topological charge has to be conserved. So the positive charge can annihilate negative charge in principle, but the net topological charge in the bulk has to be conserved. The charge can be injected through the edges, through this side of the wire and through this side of the wire, but as long as this topological charge is injected in the bulk, it has to be conserved. So we actually, and this type of free energy can actually be realized. So we checked that in TMIG nanowires, exactly such type of anisotropies can be realized. And in addition, we can also have Zoloshinsky-Mori interaction. So what Zoloshinsky-Mori interaction does here, it gives preference to one of the topological charges because it favors one sense of rotation over the other sense of rotation. So this is the type of model that we considered in this study. So the domain walls were treated as tiny particles where we used, again, collective coordinate type approach. And we also considered finite temperature where there was a random force with this type of correlator acting on these domain walls. So which means that the domain walls were essentially diffusive. They were diffusing throughout the wire, but this diffusion was kind of interesting. And the interesting fact was that the topological charge is conserved. So as a result, we could write the density of positively charged domain walls, subtract density of negatively charged domain walls, and write down the continuity equation for this type of topological charge, where rho here is topological density and I is the topological current. Now, we are familiar with the system with conserved charge. For example, electrical current is conserved, and that's why we have Ohm's law, where we have algebraic, in a way we can say we have algebraic decay of, for example, properties of for example, the signal that we transform with charge current. So then the same type of behavior should also be expected in such type of system. And in fact, when we try to solve this type of equation, introducing some diffusion into this system, diffusion constant into this system, and furthermore introducing some injection through the edges. So I don't want to go through mass here in details. So the point here is that the behavior is kind of really analogous to real electrical circuit, where the topological charge can be written as some effective voltage, which is determined by the leads and the resistance of this magnetic wire, where resistance would be the denominator of this expression, which is essentially the most important part is this proportionality to the length of the wire. So it indeed behaves as a resistance. All right, so this is kind of was an interesting result. And furthermore, another interesting result was that due to Dzerzhinsky-Mori interaction, this current response, topological current response, was actually non-reciprocal. All right, so then let me try to convince you that this type of physics can actually be realized in a real system where we just tried to take TMIG nanowire and took realistic parameters corresponding to such nanowire, where there is anisotropy that can be actually controlled by strain in such type of system. And in addition, if we take the proper shape of such wire, we can combine this type of anisotropy Ku with the shape anisotropy, and it is realistic to have exactly two anisotropies, where K will be the largest anisotropy and kappa will be smaller anisotropy, where this type of numbers would correspond to the nanowire with widths 8 nanometers and widths 40 nanometers and thickness 8 nanometers. So we also took other parameters that correspond to TMIG, because it is also known that TMIG can have small Dzerzhinsky-Mori interaction, and it also has this typical Gilbert damping 0.01. So we try to simulate such type of nanowire in the context of this type of physics, and indeed we see non-reciprocal behavior, which is shown here by these blue dots. So clearly we see non-reciprocity. However, there is a disagreement with analytical results, which here shown by this green curve. And the difference appears beyond these orange lines. So if we look deeply at what these orange lines correspond to, it's actually not hard to notice that we have a barrier which prevents us from injecting the main walls into the wire. And essentially the process that we described analytically correspond to thermally activated injection of such domain walls. However, if the charge current is strong enough, then we can push the domain wall so hard that we are not having anymore this thermally activated injection of the main wall, and it becomes essentially viscous injection of the main wall. And this transition exactly happens around these orange lines, and you might ask why there is this asymmetry here. So asymmetry exactly appears from the Dzerzhinsky-Mori interaction, and we can actually estimate this critical currents through the parameters of the system, where theta is the spin Hall angle for for example, heavy metal wire that is used for injection of the spin current. So essentially, here we are realizing diode-like behavior. For example, if you choose current to be 0.5 here and 0.5 here, then on this side of the system, essentially the system is open and there is no barrier for the injection of the main walls, and they are injected in a viscous type of process. However, on this side, we still have a barrier, and it has to happen through thermally activated process. So you might ask, what is the temperature here? Because clearly temperature would be important for such type of process. So for this simulation, we actually chose room temperature, and that's why this asymmetry is not as large. But if we keep lowering temperature here, then clearly here we would expect that this curve on the left will go closer and closer to zero. So we will get more diode-like behavior here. Okay, let me conclude at this point. So diffusion of the main walls with conserved topological charge can lead to superfluid-like spin transport. So by superfluid-like here, I mean that it can propagate over large distances described by algebraic decay. Zolshitsky-Moore interaction introduces asymmetry for positive and negative topological charges in this type of process. And micromagnetic simulations confirm this non-reciprocal superfluid-like transport in the presence of DMI. And potentially, we could use other type of solitons to realize type of physics. In particular, what we are looking at is systems where we would be able to simultaneously have skyrmions and anti-skyrmions. Then clearly there we could have this topological charge conservation. And if both of those charges can coexist together, then in principle, we should be able to realize similar type of physics. All right, so let me, I think I'm almost running out of time. So let me briefly mention our other efforts about realizing topological magnetic systems in various materials. And here in this collaboration, we use van der Waals system, where the idea was to try to lower symmetry as much as possible. So it is known that traditional skyrmion essentially appears, for example, a Neal-type skyrmion appears in system where we basically break the mirror symmetry. And it is also known that if we lower symmetry, we can potentially realize anti-skyrmion. And if we lower symmetry even further, we can actually realize what is called bimirror. So let's look then at system that is considered here, where here we consider chromium iodine 3 van der Waals magnet, which is a single layer would look like this. But then let's combine these two layers, and the upper layer will be mirror of the lower layer, where the mirror is shown here. So in principle, this is not how these layers are found in 3D structures. So we would need to perform 180 degrees rotation of the upper layer in order to realize this situation. But potentially, this could probably be realized in the lab. And then we will realize this type of system. However, clearly, this mirror will kill all efficient DMI interaction here, and it will not be suitable for skyrmion realization. However, luckily, this is not energetically favorable system, and what will happen, it will try to slide away from this configuration, developing polarization up or down, electrical polarization, and clearly that would also lower the symmetry of this system, which was initially unsuitable for realization of skyrmion. Here, the symmetry will be lowered, and it will be lowered substantially to CM prime, which actually even compatible with realization of bimirrons. However, the band structure calculations showed that the relevant DMI components were not strong enough to stabilize bimirron. However, interestingly enough, the DMI interactions were strong enough to realize anti-skyrmion in such system, and even elongated skyrmion. So because of this lower type of symmetry, the elongation became possible, and this was discussed in this paper. Then we also explored other ways of controlling skyrmions or creation of skyrmions, and in particular here we considered a balance between Dzerzhinsky-Mori interactions and dipolar interactions. And this became possible because the Dzerzhinsky-Mori interaction was induced in a gradient cobalt platinum alloy, where the gradient actually results in the Dzerzhinsky-Mori interaction. This Dzerzhinsky-Mori interaction in principle is a boring type Dzerzhinsky-Mori interaction that results in ordinary skyrmions. But what's interesting here is that because these layers can be very thick, 10 to 20 nanometers and even thicker, the dipolar interactions are very strong here, and we can control the helicity of such skyrmions. So as a result, we have the system where there is additional control of skyrmions that can be realized in this system. And finally, I arrived at the end of my talk, and I hope there are some questions.
Thank you very much, Alexey, for this interesting talk. Please thank the speaker using the reactions button in Zoom. The talk is open for questions. If you have a question, please raise your hand and wait to be called upon. Achintia, please go ahead and ask your question.
Hi. First of all, thank you for the talk. I had a simple question about the parallels you were making with just Ohm's law. That was very interesting, but I was wondering how far could you take that analogy? Because like I started thinking of like simple things like Joule heating, for example. Would your system exhibit that kind of thermal effects or beyond? I don't know.
Yes, so here clearly we would have some dissipation because there is Gilbert damping in the system. Some certain dissipation, of course, will be arising in this system. So, and the resistance also leads to some dissipation. So, yeah, you can make such analogy.
Would you warn against, like, for example, I'm guessing the analogy would break at some point for certain things. Like, would you have a note of caution?
Analogy, yes, it can break, for example, due to thermal slips. So if temperature, for example, is large enough, then we can have a process where this type of topological charge can unwind through by going out of ZX plane, right? So that would be deviation. So this topological protection is enforced by this anisotropy K, and the topological charge would only be conserved at low enough temperatures. We start going to higher temperature, yeah, there will be deviations where we at high enough temperature we will then we'll get exponential decay again.
Okay. Thank you.
Okay, thank you. Other questions, please? So, Alexey, in your discussion of the skyrmion Hall effect in ultramagnets, do I understand correctly that the Hall effect depends on the orientation of the charge current in the crystal?
Yes. So
in which cases is it finite, and in which cases is it zero? I think you
okay.
may have mentioned that, but it's
so when we this zero angle with 110 direction, which I marked here. So if
generally that's a direction where the longitudinal charge current is unpolarized.
No,
right?
So this direction. So 110 direction, that's where we see the largest skyrmion Hall effect. So zero. So this is angle with respect to that 110 direction.
Oh, okay, yeah. So V1, okay. So that's when the charge current is spin polarized to get the maximal
yes,
Hall effect.
yes. And it dominates, actually. The transversal velocity is much, much larger compared to the longitudinal velocity. So it is known that we cannot drive efficiently skyrmion with this non-adiabatic spin transfer torque, but in the transversal direction, we can actually drive them much, much faster.
Okay. So the fact that there is a transverse spin current for the directions where the longitudinal charge current is not polarized, does that play any role in the skyrmion motion?
I mean, it does, because for this 45 degrees orientation, would be that case, we get much faster motion. So it is mostly driven by that in polarized current, actually. Yeah, so at this 45 degrees point, and maybe if you want to create a device, this would be the sweet spot. Because here you're still driving skyrmion along the current direction, and you're driving it very, very fast. So this would be useful for, like, I don't know, magnetic memory applications.
So you're saying it's essentially the second term that's driving it?
Yeah, essentially the spin splitter torque is driving it, yes, for this type of orientation, yeah.
Okay. Thank you. Shen, please go ahead.
Hi, Alexey. Thank you very much for the talk. I have a question about the formation of the skyrmions. I'm not really familiar with this field, but I thought in ferromagnets, the skyrmions can be formed because of the competition between exchange and dipole interaction. Now, in collinear antiferromagnet, there's really no dipolar interaction. So you will need to involve some other things to stabilize the skyrmion. Is that correct?
Yes, you're right. So we kind of made the leap here, and we did assume that we, for example, took our layered altermagnet and placed it maybe on heavy metal to create the correct mirror type break-in symmetry. And so here you would need to go the ordinary route of inducing DMI by properly engineering the structure. So it will not be enough to have just altermagnet, at least for this type of DMI that we consider.
I think you can have DMI, but if there's no dipolar interaction, wouldn't the ground state be just everything be aligned in the same direction? Why would they actually form the domain?
I mean, by symmetry, yes, you can have some DMI, but I don't think it can be used to stabilize skyrmion.
Okay. So in your system, you assume the skyrmion is already formed, and then we can use the spin split force torque to move it around.
Yes. So yes, we assume that we have. In fact, we assume the normal type of DMI that, for example, appears in ordinary ferromagnets. Similar type of DMI. Yes.
Sure.
But here there could be some interesting, I guess, additional effects due to symmetry, and that is worthwhile looking at. What type of DMI we can have here, and how this will affect skyrmions.
Sure. Okay. Thank you.
So maybe for experimentalists, it would be easier to look at domain walls where you don't need DMI.
Sure. Even domain walls in antiferromagnets are mostly driven by if of a stress or defect or anisotropy. So moving domain wall around is not as smooth as in ferromagnets, as far as I understand.
Yes, but it's always good to have extra mechanism, right, to control them.
Of course, yeah. Thank you.
Yeah.
Hey, Kai, you're next.
Thank you, Professor Alexey. Cool. It's a nice talk. I want to ask. I want to make a note that before still about this topological particle in the automatic. There was another paper also published in PRL last year by Yan Peng from the Electronic Technology University in China, and they do similar thing as you did, calculating the dynamics of the skyrmium in the automatic material. But it seems that they didn't include the spin splitter effects, spin splitter torque effect. So can you again emphasize what's the importance of the spin splitter effect here, and if without it, just using the spin transfer torque, what kind of the mechanism the topology the skyrmium is?
So we tried to reproduce that paper and we could not numerically or analytically. And I think there is a mistake in that paper. So the effect that they describe basically is negligible for typical parameters that would be relevant for ultramagnet. That was our conclusion. So you need spin splitter torque to induce skyrmion Hall effect.
So if with the absence of the spin splitter effect, the result will be trivial or just wrong, or?
So there could be very small skyrmion Hall effect, but it would require a huge amount of current. It would require deforming your skyrmion into some elliptical shapes. It's like, I don't think it's experimentally realistic to induce skyrmion Hall effect in that way. I mean, maybe one system where that paper could be relevant to would be a synthetic antiferromagnet where you would take 2 layers, because then you can control the interlayer coupling and you can make it weak, right? The antiferromagnetic coupling between 2 layers. But then you also need to somehow induce this exchange anisotropy. So I don't know if it's maybe in some van der Waals systems, I don't know. But basically, the only route of realizing that type of physics I see maybe in synthetic antiferromagnets. So I'm just saying we could not reproduce those results, and the only way we could induce a skyrmion Hall effect was by spin splitter torque.
Okay, thank you.
Okay, are there any other questions? All right, if not, let's thank Alexey again. And thanks everyone for coming. We're going to stop the recording and streaming in a few seconds, but if you would like to stay for a little informal discussion, you're welcome to do so. Just give me a second.